Chapter 2, Elements and Compounds. Douglas Cardinal is an architect who often creates models of structures to give shape to a concept. Architects use models not only to help them uncover design problems and to solve them, but to make the concepts much easier for other people to understand and visualize. Have you ever built a model? What did it teach you? Brainstorm a list of the possible uses of models. In science, models are not just physical constructions. A model can be a diagram, it can be a classification system, a mental picture, a theory. In fact, a model is any means of representing a thing or a process. Models are made see, or things we find difficult to understand. What scientific models are you familiar with? Choose one and ask yourself what the model seeks to explain and how complete the explanation is. Number 3, a Montreal woman is helped from her home during the 1998 ice storm. Emergency generators used to provide electricity spread carbon monoxide fumes through her apartment complex. Carbon monoxide is a poisonous gas that kills people every year. How can the particle theory help us understand substances like carbon monoxide? The particle theory suggests that matter is made of basic building blocks called elements. An element is composed of only one kind of atom. Atoms can be assembled in different ways. For example, carbon and oxygen. Atoms can be combined to form the gas you exhale with every breath, carbon dioxide, or the dangerous gas that affected this woman, carbon monoxide. What other combinations of atoms are you aware of, and how can they affect our daily lives? Models of matter, the particle theory. Observing and experimenting with matter has led scientists to theorize about what matter really is. Their working definition of matter is anything that takes up space and has mass. When we observe matter, we can see it behave in countless ways and can put it to countless uses. But is matter one definable thing? Over the centuries, scientists have created many models to explain what matter is, to explain what lies beyond what we can physically observe. One of the most enduring models of matter is the particle theory. Building blocks of matter, the particle theory. More than 2,000 years ago in Greece, a philosopher named Democritus suggested that matter was made up of tiny particles too small to be seen. He thought that if you kept cutting a substance into smaller and smaller pieces, you would eventually come to the smallest possible particles. The building blocks of matter. The basic principles of the particle theory are reviewed in Table 1. Let's go to Table 1. So, the particle theory of matter, principle and illustrations, 2 columns. So 1, all matter is made up of tiny particles. So there's a little bit of a blow up of the corner of that cube. Number 2, all particles of one substance are the same. Different substances are made of different particles. So we have substance A, that's all uniform. We call it pure. A substance is pure matter, pure material. A substance is either a compound, or an element. Then you have substance B, the green one. And then number 3, it says, the particles are always moving. The more energy the particles have, the faster they move. They all have kinetic energy. Kinetic energy equals 1/2 the mass times the velocity squared. So, if it's hot, it's moving very fast. If it's cold, it's moving slower. There are attractive forces between the particles. These forces are stronger when the particles are closer together. Particles far apart, force is weak. Particles close together, force is strong. Pure substances and mixtures. Using the particle theory, we can understand that categories of substances, pure substance and mixture. A pure substance contains only one kind of particle. For example, a piece of aluminum foil contains only aluminum particles. Sugar is a pure substance. It contains only sugar. A scoop of sugar from Canadian sugar beets contains exactly the same kind of particles as a scoop of sugar made from Australian sugarcane. A mixture contains at least 2 different pure substances or 2 different types of particles. When you drink a glass of milk or eat a cookie, you're consuming mixtures of different substances. Most common substances are mixtures. Figure 1 shows the relationship between substances and mixtures. All right, let's look at figure 1. All right, so down below, we'll read the caption first. It says, pure substances. Pure substances contain only one kind of particle. It's going to be either an element or a compound. All right, B, mixtures. When 2 pure substances are mixed together, sometimes they are mixed smoothly and sometimes they mix unevenly. If the particles mix very well with one another, so well that you can only see one phase or one visible part, the mixture is called a solution. So a phase is a single set of physical boundaries. You say that one substance dissolves in another. If the particles don't mix well with one another, you will see more than one phase, more than one set of physical boundaries. This type of mixture is called a heterogeneous mixture. So a homogeneous mixture is a solution, a complete combination. So homogeneous can be used 2 ways. A homogeneous set of material, for instance, a substance is homogeneous. It's just gold, it's just water, it's just sodium chloride. Or a homogeneous combination of 2 or more substances resulting in one phase or one set of physical boundaries. So homogeneous can be used in 2 ways. Heterogeneous can also be used in 2 ways. You have a heterogeneous compound made of 2 different elements, but it's one substance. You can also use heterogeneous in terms of taking 2 substances and mixing them heterogeneously, so you have 2 phases. That's also a use of heterogeneous. Okay. Figure 1, again, figure 1 shows the relationship between pure substances and mixtures. So if you look at the figure itself, A, pure substances, okay, that's on the left. So, for instance, just gold, where you just have gold atoms, or just iron, you have just iron atoms. Or when you have a mixture, you can have a solution, a homogeneous mixture, or you can have what we call a mixture, a classical mixture which is a heterogeneous combination of two substances resulting in two or more phases. Classifying mixtures. Imagine you have a sample to identify that you think is a mixture. What type of mixture might it be? Perhaps your mixture is a solution, like sugar and water. If you add a small amount of sugar to water and stir, the sugar disappears as it dissolves. A solution may be made up of liquids, solids, or gases. Air is a solution of gases. Perfumes are a solution of alcohol and fragrances. Many alloys are solutions of solid metals. The sample of matter may be a heterogeneous mixture, like pizza. When you make a pizza, tomato, sauce, cheese, mushrooms, pepperoni are mixed together or scattered on top of the crust. Each part can be easily seen. Garden salad, where you have tomatoes, onions, garlic, oil and vinegar. Garbage. These are all heterogeneous mixtures. Elements and compounds. Many properties of matter can be explained by using the particle theory. But what are these particles? 200 years ago, scientists like the one in Figure 2 already knew of thousands of pure substances and were constantly discovering more. Scientists hope that by breaking down these substances, they would discover the building blocks of matter. The particles that Democritus suggested couldn't be broken down any further. Once they knew all the building blocks, they believed they would be able to predict the properties of pure substances from the properties of the blocks or particles of which it was made. Figure 2 shows a gentleman and a younger person working in an old-style laboratory. Using equipment like this, scientists of several centuries ago conducted experiments on matter. As a result of these efforts, scientists now know of over 100 of these building blocks, which are called elements. Elements are pure substances that cannot be broken down into simpler substances. Water, which is formed from two of these elements, hydrogen and oxygen, is called a compound. Compounds are pure substances that contain two or more different elements in a fixed proportion. They're formed when elements combine together in chemical reactions. For example, in water, there are always twice as many particles of hydrogen as particles of oxygen. Table 2 shows how the classification of matter can be expanded to include elements and compounds. Let's look at Table 2. Pure substances and mixtures. Elements in substance. Element A, alone. Type of substance. Pure substance, an element. Description, only one element is visible. Elements A and B. Pure substance, compound. The compound may have completely different properties from each of these elements. The elements are chemically combined. Mixture, solution. The solution may look very similar to one of the elements, as particles of the other element are hidden within it. Mixture, heterogeneous. Particles of each element can be seen separately. Atoms and elements. How can we use the particle theory to understand elements and compounds? Once again, water provides a clue. At one time, people thought that water was made up of particles that could not be broken down further. We now know, however, that water can be broken down into hydrogen and oxygen, and that when we measure the volumes of the gases, we always get twice as much hydrogen as oxygen. One water particle is formed from the particles of two elements, two particles of hydrogen and one particle of oxygen, as shown in Figure 3. Figure 3, a model of water molecule. Scientists now call the particles in the particle theory atoms. Each element is made up of only one kind of atom. Since there are more than 100 elements, there are more than 100 kinds of atoms. This book is 20 years old, so there's a lot more elements than when this book was first written. Molecules. Atoms join together in combinations. When two or more atoms join together, a molecule is formed. Molecules can contain two atoms or many thousands of atoms. The atoms in a molecule can be all the same kind of atom. For example, in the element of oxygen, there are two oxygen atoms in each molecule. Molecules can also be made of two or more different kinds of atoms. For example, a compound called butane, a fuel, contains 4 carbon atoms and 10 hydrogen atoms in each molecule. Models of molecules. Examine the models of molecules shown in Figure 4. Let's look at Figure 4. It's in 3 parts, A, B, and C. A. Atoms of the element oxygen join together in pairs, forming oxygen molecules. In the compound methane, the main component of natural gas, each molecule contains 1 carbon atom and 4 hydrogen atoms. In acetic acid, vinegar, each molecule has 8 atoms, 2 carbon atoms, 2 oxygen atoms, and 4 hydrogen atoms. Let's reread the last sentence. Examine the models of molecules shown in Figure 4. The first shows a molecule that contains 2 atoms of oxygen. This is a molecule of the element of oxygen. The other 2 show molecules of compounds. All right. When hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, when they're in the gaseous state, they are diatomic. So it's H2, N2, O2, F2, Cl2, Br2, I2. When they're in the gaseous state, they exist diatomically. Different molecules from the same elements. In compounds, atoms of one element join together in fixed ratio with atoms of another element. For example, when hydrogen and oxygen combine in a ratio of 2 to 1, the compound they form is always water. What happens if hydrogen and oxygen combine in a different ratio? The result is a different compound with different properties. In nature, there is only one other compound that contains only hydrogen and oxygen, hydrogen peroxide. In hydrogen peroxide, hydrogen and oxygen atoms are in a 2 to 2 ratio, or 1 to 1 ratio, as shown in Figure 5. Let's look at Figure 5. A hydrogen peroxide molecule has 2 hydrogen atoms and 2 oxygen atoms. Compare this with the model of water shown in Figure 3. The properties of water and hydrogen peroxide are very different. Water is everywhere on Earth, part of all living things. Hydrogen peroxide is a much more reactive compound. In Figure 6, it is shown interacting with a drop of blood. Figure 6. A hydrogen peroxide solution bubbles as blood is added. Hydrogen peroxide is used in antiseptics. It bubbles when it touches dirt or blood in cuts or scrapes. Water in a similar situation does not react. Hydrogen peroxide solution used as an antiseptic is 3% hydrogen peroxide. So it is a solute, and the solvent is water. So it's a 3% solution of hydrogen peroxide and water. That's what you use as an antiseptic. Other elements can also be combined in different ratios to produce different compounds. For example, acetic acid, vinegar, contains atoms of hydrogen, oxygen, and carbon. These same elements also combine to form many other compounds, including sugars and fats. Understanding concepts. 1. Use diagrams to explain the difference between a pure substance and a mixture, a solution and a heterogeneous mixture. A pure substance and a mixture. A pure substance is either an element or a compound. A mixture is a combination of two or more materials resulting in one or more phases. For instance, you can have a heterogeneous mixture, which is commonly called a mixture. You can also have a homogeneous mixture, which is called a solution. You can also have pure material that's homogeneous, like gold, or heterogeneous material that's a substance, such as sodium chloride. A solution and a heterogeneous mixture is, like I just said, a solution is a combination of two or more substances resulting in one phase, such as sugar and water, or rocks and sand is a heterogeneous mixture. Create a summary chart for the concepts in this section: elements, compounds, atoms, mixtures, molecules. Include the following headings: term, definition, and example. I'll let you do that on a poster. Give examples of two molecules that are made from the same types of atoms. I'll let you do that as well. Give examples. State whether, number 4, state whether, 4, state whether each of the following pure substances is an element or a compound. Explain your reasoning. A clear colorless liquid that can be split into two gases with different properties. B, a yellow solid that always has the same properties and cannot be broken down. And C, a colorless gas that burns to produce carbon dioxide and water. I'll let you do those as well. Reflecting. Look back to the try this activity in getting started. Are there any changes you would make in your answers? Putting metals to work. You have investigated the classification of elements as metals and nonmetals based on their physical properties, figures 1 and 2. Similar characteristics can be observed in their chemical behavior. The physical and chemical properties of metals make them very useful substances in many applications. Because copper and aluminum conduct electricity well, they are used in wiring and electrical circuits. The lack of reactivity in gold and silver make them valuable in jewelry. The hardness and strength of metals make them useful in buildings and automobiles. Their ability to be shaped easily and conduct heat have made them useful for centuries in cooking pots and utensils. Metals in industry. People have used metals for tools and jewelry for thousands of years. More recently, many other uses have been found for different metals and mixtures of metals. For instance, platinum is a very unreactive metal that can be used in precision instruments. Uranium is a very dense metal that is used in nuclear power plants. Many less dense or light metals also have useful applications. Sodium can be used in chemical reactions. Magnesium is a light, strong metal that can be used in automobile wheels and luggage, especially in cases designed for photographic equipment, which requires extra protection. Aluminum pots and pans are sometimes used in the kitchen because of their lightweight and good heat conductivity. One group of metals is shown in Table 1 and Figure 3. These elements are called heavy metals because they show the typical shininess and other physical properties of metals, as well as having very high densities. Many of these elements are more than 4 times as dense as water. Compounds of many heavy metals are essential in small amounts in healthy plants and animals. However, in larger quantities, they can cause damage to living things. Heavy metal compounds may be absorbed directly from the air or water through leaves, roots, skin, lungs, or gills. Animals can also absorb them from the organisms they consume in normal food chains. A predator eats many small animals over time and may accumulate poisonous levels of metal compounds in the liver or other organs. Generally, concentrations increase up a food chain from plants to herbivores to carnivores. For instance, fish, tuna, will accumulate large quantities of heavy metals during their lifetime. You've got to be careful when you eat certain fish. Lead is a heavy metal that can have damaging environmental effects. Lead poisoning can harm the nervous system and the brain. Until the 1960s, lead was often used in drain pipes, in paints, and even in gasoline. Unfortunately, young children sometimes ate flakes of paint, and people of all ages were harmed by inhaling lead-containing dusts from automobile exhausts. Today, most drain pipes are made from plastics and alternative paints, and lead-free gasolines have been developed. Mercury, shown in Figure 4, is a heavy metal that can be dangerous. Heavy metals in the environment today can come from many sources: industries, mining operations, and power plants. Must take care not to carelessly release substances into the air or water. Figure 4. Mercury metal is unusual because it is a liquid at room temperature. Discharge of mercury compounds into the environment from pulp mills and industrial plants is dangerous because mercury damages the nervous system of fish and humans. It is also used in mining certain precious metals. Understanding concepts. Make a chart listing the properties of metals and nonmetals. I'll let you do that. 2, A and B. Why are some elements called heavy metals? Give examples, this is B, give examples of 3 heavy metals and list their uses. Making connections. 3. Elements are chosen for various uses. Research and write a summary paragraph explaining the following choices of elements. A. Copper is better than aluminum in most electrical wiring. B. Lead is no longer used in the manufacture of food containers. C. Mercury is no longer used in most thermometers. And D. Titanium is used in aircraft wings. Exploring. 4. Record the substances described as minerals that are listed on the label of a multivitamin from your medicine cabinet or a local pharmacy. Make a graph and identify which elements are provided in the largest amounts. 5. Plumbers and electricians work with copper metal as well as solder, a mixture of metals used to join metals together. Find out how they choose particular metals to use for specific purposes. Testing for elements and compounds. Imagine that you are a technician in a chemical lab. While cleaning up after a flood in the laboratory, you discover that the labels of 3 gas cylinders have been damaged. You suspect that the cylinders contain carbon dioxide, oxygen, and hydrogen. How could you find out which cylinder contains which gas and whether the cylinders have been contaminated by flood water? Do they now contain water vapor? 4 common tests are used to identify 4 common gases. A. Why would it be difficult to identify the 3 gases by their physical properties? Oxygen, the glowing splint test. One common chemical reaction is combustion, burning. Oxygen must be present for combustion to take place. Substances such as wood and oil burn readily in air, which is about 20% oxygen. In pure oxygen, they burn much more intensely. This chemical property of oxygen, supporting combustion, allows you to identify it. You could test for it as follows. Figure 1, the glowing splint test for oxygen. Light a wooden splint. Blow out the flame, but leave the splint glowing. Hold the glowing splint in a small amount of unknown gas. If the splint bursts into flame, the gas is oxygen. B. Why should you blow out the flame first? C. Why should you only test a small amount of gas? And D. Do you know of any other gases that would give a similar result? Hydrogen, the burning splint test. You may have already used the second test, figure 2, which says the flaming splint test for hydrogen. You may have already used the second test, figure 2, based on hydrogen's explosive reaction in air. This test should be attempted on only a small amount of gas in an open-mouth, shatterproof container. It should be done only under teacher supervision. Safety goggles should always be worn. Light a wooden splint. Hold the burning splint in a small amount of unknown gas. If you hear a pop, the gas is hydrogen. E. What property of hydrogen are you testing for? Why should you only test a small amount of this gas? Which should you test for first, oxygen or hydrogen? Why? If the flame goes out, what can you say about the identity of the gas? Carbon dioxide, the lime water test. Carbon dioxide does not burn and does not allow other materials to burn. If you put a burning splint into carbon dioxide, the flame will go out. The chemical test for carbon dioxide uses a liquid called lime water, a clear, colorless solution of calcium hydroxide in water. Carbon dioxide reacts with the dissolved carbon hydroxide, producing a precipitate, figure 3, the lime water test for carbon dioxide. A precipitate is a solid, insoluble material that forms in a liquid solution. The precipitate causes the lime water to appear cloudy or milky. If you suspect that one of the cylinders contains carbon dioxide, carry out this test on a small amount of gas in a test tube. Bubble the unknown gas through lime water solution, or add a few drops of lime water to the solution and swirl it around. If the lime water turns cloudy or looks milky, the gas is carbon dioxide. I. Do you think oxygen or hydrogen would also turn lime water cloudy? Why? In what order would you carry out these 3 tests? Water vapor, the cobalt chloride test. Water is a liquid at room temperature, but many chemical reactions produce water vapor as a product. When water vapor touches a cold surface, it condenses to liquid water. To test for the presence of water, use the following test. Figure 4, the cobalt chloride test. There's cobalt chloride paper, indicates the presence of water when it turns pink. Hold a cold surface near the suspected water vapor. Touch a piece of cobalt chloride paper to any liquid that condenses. If the paper changes from blue to pink, water is present. K. Is it likely that there would be water vapor in the cylinders? Why? Understanding concepts. 1. How would you test for the gas produced in each of the following, and what observations would you expect to make? A can of pop fizzes, that would be carbon dioxide, lime water test. A nail added to a strong acid produces a combustible gas. Acid is hydrogen plus either a halogen or a negative ion, or hydrogen plus a polyatomic ion, so there's always hydrogen there, so you test for hydrogen. C, when potassium chlorate, which is KClO3, is heated, a gas that supports burning is produced. That is most likely oxygen, and you would use the glowing splint test. 2A, if you placed a glowing splint in a test tube full of clear, colorless gas and the glowing stopped, which of the gases discussed here is most likely present in the test tube? It would be carbon dioxide, which does not support combustion. How could you confirm the identity of the gas? With a quick lime water test. Exploring. Gases such as those mentioned in this case study can be a safety hazard, especially if people are not aware of their properties. Research how labeling, color coding, and other systems are used so that gases
can be handled safely. Create a poster to communicate this safety information to others. I'll let you do that on your own. That would be an assignment. Number 4, the gases hydrogen and helium are both less dense than air. So either gas may be used in lighter air ships, lighter than air ships. Use references to research what properties hydrogen and helium have in common and in what ways they differ. Explain why modern blimps are filled with helium gas instead of hydrogen. Well, look up the Hindenburg disaster at Lakehurst, New Jersey, near where I was born and raised, and why Germany had to use hydrogen. It had to do with the United States.